And you can do that with zero-dimensional manner, or one-dimensional, two-dimensional, or three-dimensional laser diagnostics are possible. That depends on how you uh, align the laser beams, how you make the light sources. See? So that's another things we have to consider. That's how to measure. Hmm? All right. So that was very typical systems you might be interested in if you're interested in working in aerospace industry or aerospace science. Hmm? But in mechanical engineering department, we have a bunch of different systems like cars, vehicles, or battery systems, or combustion systems, gas turbine systems. In all these the systems currently used actually utilize very complicated flow. For example, laminar flame and laminar flow are not our main interest anymore. Those are very helpful for theoretical approaches, but those are not actively used for real systems. Even with cars or vehicles, the flow around it is becoming turbulent because the flow speed is so fast and the vehicle can move at very high velocity, and that is causing much more complicated three-dimensional flow field. And to understand these three-dimensional flow behaviors or combustion behaviors or thermal uh, trans- transportation or some more complicated phenomena, we should use optical diagnostics. So the demands for optical diagnostics is now increasing. So that's why we need to understand or be knowledgeable about laser diagnostics method. But as I told you, the laser diagnostics or optical measurement method is quite expensive. So we want to minimize the expense for this measurement. So, for example, once you decide what kind of system is your interest in, what kind of properties or uh, quantities you want to measure, then next thing you should do is to determine what to measure. Okay? Here's an example. Another example. So this is a rocket design. So high pressure and high temperature gas will be produced in the combustor, and those gas will be emitted through the CD nozzle, converging and diverging nozzle. And the gas, high pressure gas, will lose its kinetic, thermal energy, but its kinetic energy will be increased. So, in other words, using this CD nozzle, the velocity will be increased, or the flow can be accelerated, and the accelerated gas will be emitted through this nozzle, and then that will produce the thrust. So maybe the most important, performance criteria of this rocket engine would be the production of thrust. So you want to measure the thrust, but there is no way of directly measuring the thrust. Okay? Maybe you can hang this engine with at a rod with a load cells, and load cells is giving you the thrust correctly. But in case the engine is too big, and if you want to measure the thrust produced by this engine while this guy is flying or under operation, okay, so it will become much more complicated. Okay? And the thrust can be estimated using this simple equation. So force, that is thrust, can be estimated with the mass flow rate m dot and velocity of the flow at the exit VE and exit pressure and surrounding pressure and area of the exit. Okay, that's what you need to measure for estimating the thrust. Okay, here PE, exit pressure, can be measured with a simple pressure sensor at the exhaust. P naught can be easily measured. Maybe the atmospheric pressure can be measured. And area of the exit can be definitely measured even before the operation. It is not changing. It is a constant. So the constant can be measured and the pressure can be easily measured. But how can you measure the mass flow rate through this CD nozzle? How can you measure the exit velocity profile on the exit plane of the nozzle? That is the key part for this measurement. Okay, so these guys maybe can be measured easily: pressure difference and the area of the exit nozzle. But velocity at the exit plane of the nozzle will not be uniform. So the non-uniform velocity field should be measured. So that means you need at least two-dimensional measurement, even though you are assuming that it is axis symmetric. with the axis symmetric assumption, maybe along a line that is passing through the center of the nodal exit plane, you can measure the velocity field, and maybe that is sufficient for estimating the velocity field on the exit plane of the nozzle. Okay, so now you need one-dimensional velocity profile measurement. Okay? And the other one is the mass flux rate. Mass flow rate can be measured at any locations, but all the mass flux should be measured. And maybe you will want to choose the smallest cross-sectional area at the throat. Okay? At the throat, there are many useful theoretical backgrounds that can give you the mass flow rate. Okay? At the throat, your Mach number will be ideally 1 because this is a supersonic nodule. The flow will be subsonic in the upstream region, and in the downstream region, it should be in supersonic regime. So for accelerating the subsonic flow toward the supersonic flow, you will need a throat where the Mach number is exactly the 1. Okay. Then what do you need here to measure or estimate the mass flow rate? Okay. For mass flow rate, what you actually need is the total pressure in the plenum chamber, assuming that there's no shock wave appearing here. So that is typically true. So no shock wave is appearing before the strut. The shock wave, in the worst case, will reside after the strut. So you don't have to worry about that. So there is no stagnation pressure loss. So the stagnation pressure at the upstream region is exactly the same at the strut. So you have PT. Okay, and your Mach number is fixed. Okay. So if you can measure the temperature at this location, then basically you know everything. Okay? You will know you will know the absolute velocity because you have the temperature. Okay? The temperature is giving the speed of sound, and your flow velocity here at the throat will be exactly the same as the speed of sound because Mach number is ideally and practically 1. So the absolute velocity will be the speed of sound. And you know the cross-sectional area of the throat. That is definitely a constant. It is not changing. Okay, you have the cross-sectional area and the velocity of the flow, pressure, and definitely you know the property of the gas that is producing the combustion. So density will be given, okay, at a certain pressure and the temperature. Static pressure can be estimated using this total pressure condition. Okay, so only one thing you have to measure is the temperature at the throat in this case. Okay? If you have the temperature at the throat, then you will get the mass flow rate. Okay, so now the system became much more simpler. I mean, much simpler than expected. So if you want to measure the thrust, what you actually need to measure is the temperature at the throat, and that can be done with the sensor, and the pressure at the exhaust, and that can be also measured with the sensor, and the velocity field along a line that is passing through the center of the nozzle exit. Okay, all right. Then you will have to find a way of measuring the velocity field along a line at the exhaust. Okay? So maybe you will try to find a way of measuring that using optical measurement method. If you put some maybe pitot tubes to estimate the velocity here, maybe you will have a kind of rake having multiples of pitot tube along a line. That could be another way of measuring that, but because the temperature is extremely high in this case, your pitot tube will be easily damaged, and that will also disturb the flows in the downstream. Okay? So you will want to measure the velocity profile using a non-intrusive measurement method. So optical measurement is mostly non-intrusive because you are injecting only the masses. There's no mass. The photons will be injected. Okay? All right. So that's a very quick example, and we will see some other examples. Okay. So as you have seen here, we have tried to simplify the measurement target systems. And this simplified system still requires some measurement. In this case, temperature, pressure, and also from the sensors, and optical measurement will be used for one-dimensional velocity profile measurement. Okay? All right. So optical measurement method can be used for measuring volume, internal energy, maybe temperature, and temperature can give you or other things. Okay? And these constants, if are given, can be used for the optical measurement method as well. Okay? So optical measurement is typically giving you the density, concentration, pressure, temperature, and velocity. Okay? So these guys, in conjunction with sensors or given by a constant as a constant, can give you the energy, force, mass flow rate, etc. Okay? So usually the optical measurement method can be chosen for measuring velocity, density, concentration, pressure, and temperature where sensors are not working. Sensors are not working. A cheaper way of measuring that. But with the proportion applications or high energy, high performance, and high speed vehicles or high performance systems, mostly sensors will not work. Yeah. Recently, new sensors have been developed, and some sensors are working at high pressure and high temperature conditions. But interestingly, as the pressure increases or as the temperature increases, in other words, your target system has higher energy, optical measurement is easier. Okay? So easier way of measuring the properties of the fluid would become optical measurement method, particularly in high pressure and high temperature conditions. So that's why we need these systems, particularly for high performance energy systems. Okay, here's another example. Okay, so it is A380. That is one of the biggest air carrier in operation. So this gross weight is 1.2 million pounds, and measuring something for estimating the performance of this guy or for studying the flow around this vehicle would be quite massive and difficult and expensive. Okay, so there are some other options you can choose, and maybe you will make a small-scale model of this aircraft and then testing it in a wind tunnel. Then you can do measurement better, and you can get much more useful information from the wind tunnel testing compared to the in-flight measurement. In-flight measurement is very limited. Let's say this guy is flying at high altitude, and this guy who should have some pitot tubes and pressure sensors and temperature sensors outside probably, and those sensors are giving, recording the flow conditions around it. But you don't have like many sensors around it, and the sensors are providing informations, but those are quite limited. Sorry, I had a visitor. Anyway, so this aircraft is an interesting target system, and for further investigation with the laser diagnostics, maybe we will build a smaller models. Okay? But there are some exceptions, like in the United States, where the aerospace engineering has been developed for a long time. They have large-scale wind tunnels. You can see this; these are just literally buildings. The buildings are connected for accommodating a large wind tunnel. And you can see a power plant here because this wind tunnel is consuming like megawatts of energy for generating those high-speed flows. And rear scale aircraft is now settled inside. So this guy is used for the measurement in the large scale wind tunnel. But it consumes huge amount of energy and it's very expensive, and a single test will maybe consume lots of money. So it's not viable for most of the research institutes. Okay, so you can see large system installed for this wind tunnel. So small scale model is still pretty good for detailed measurement. So for example, you are looking at a small scale aircraft, not a real scale. So in this case, maybe you will keep the flow velocity high enough, but the length scale is now reduced. That means Reynolds number will be reduced. If the Reynolds number is reduced, then turbulence behavior or turbulence transition in the boundary layer will be different. So we should think about the dynamic similarity in this case. But if you're considering this kind of similarity issues, measurement will get much easier. So now you can install the laser systems around it, and you can put more sensors around it, and also you can visualize the flow around the aircraft easily. So that will be really helpful for studying the behavior of the flow around this aircraft, and that will potentially will help to improve the performance of this aircraft, or maybe to improve the design of the aircraft. All right, so this is subsonic flows, and if your vehicle is designed for flying at high Mach number, like supersonic or hypersonic flights, then the small-scale testing is becoming also challenging. In this case, you will have to produce a high speed and decent temperature flows around your vehicle model. So now, let's say you have a small-scale model, but wind tunnel design is becoming much more complicated. And in this case, your measurement is becoming more important because your flow is too fast, and to produce this fast flow at a decent temperature, you will have to heat up the gas in the upstream so high. So maybe some molecules will be dissociated and some molecules could be excited, and that will make some difference in your experiment. So optical measurement is becoming more important, particularly for high-speed aircraft testing. Let's say here's a simple equation here, and total energy of the flow is expressed like this. So with the high-speed flows, definitely those flow will have an internal energy in the upstream and internal energy in the downstream, and the velocity difference could be quite large, even compared with the internal energy. Typically, internal energy is much larger than the kinetic energy of the gas, and the typical velocity where the kinetic energy is negligible is like Mach 0.1 or 2. So Mach 0.1 or 2 is still fast velocity, like 30 meters per second or 60 meters per second, let's say. So that is quite fast flow, but still the kinetic energy of that flow is almost negligible compared to the internal energy. But if the Mach number exceeds like 1, 2, or for hypersonic vehicles like 9 or 10, your kinetic energy of the flow is even larger than the internal energy. So in that case, the high-speed air, contains a huge amount of energy. Okay? So let's think about the hypersonic wind tunnel. And for the hypersonic wind tunnel, in the downstream where the test section is placed or your vehicle model is placed, kinetic energy should be really high. But maybe the internal energy will be low. And in the upstream region where the flow is nearly maybe kinetic energy would be negligible. Only the upstream internal energy should be the summation of the downstream internal energy plus kinetic energy. And this kinetic energy is large. So that means to keep the temperature of the gas in the test section decent, like 200 Kelvin or 300 Kelvin, your upstream temperature should be very high. So here's an example. So let's say you are heating up the gas in the upstream chamber up to 4,000 Kelvin, and the pressure is like 10 bar. And that gas is now stored. And producing that kind of gas is extremely difficult. The pressure is high and the temperature is 4,000 Kelvin. And remember that the typical combustion temperature is only 2200 Kelvin. So 4000 Kelvin is not the temperature reached with the combustion reactions. Only the plasma discharges can produce that kind of high temperature. Okay. Now you are producing Mach 9 flow with this high temperature gas. Okay? And then your upstream high internal energy corresponding to the 4000 Kelvin will be dropping to U downstream, and most of this energy will go to the kinetic energy. At Mach 9, your flow speed is so fast. Okay? Then your test section static temperature would be only 230 Kelvin. 230 Kelvin from 4000 Kelvin, because most of the thermal energy now is converted into the kinetic energy. So that kinetic energy is to used for accelerating flow up to Mach 9. So the pressure will be dropped down to 0.35 torr. Okay? 100 bar is 7600 torr. So from 7600 torr down to 0.35 torr. So that's a quite drastic change of pressure. Okay? And from 4000 Kelvin down to 230 Kelvin, that is also another drastic change of temperature. Okay. So then you will need an intensive heating source for generating this kind of high temperature and high pressure gases. Okay. Is there any sensors that can measure the temperature like over 3000 Kelvin? Maybe not. Even the tungsten melting point is lower than 4000 Kelvin. So physically, no sensors will be working for these high temperature conditions. Then what kinds of sensors can be used for Mach 9 flows? Mach 9 flow is so fast, so it is moving like kilometers per second, okay? Several kilometers per second. So it is so fast flow. So if you inject maybe insert a physical sensor into it, your sensor will be broken, or it will cause a strong shock wave, and then it will mess up your flow. Okay? So only the optical measurement method can be used for measuring the properties of this high temperature or high speed gas. Here's some more examples. So flow velocity is a red curve, and the static temperature is blue curve. And static temperature is exactly proportional to the internal energy. You know that CEB multiplied by the temperature is representing the internal energy. So internal energy and the kinetic energy in this case are the total energy, let's say, and then as the velocity increases, your static temperature will decrease, so that the total energy is kept constant. So some heaters utilize combustion reactions. So in this case, maximum temperature is like 2000 Kelvin. It's a still decent temperature. Maybe you can simulate Mach 5 or 6 conditions, maybe 7 conditions. But measuring this high temperature is not easy neither. So maybe you might want to use optical measurement method like laser absorption spectroscopy or laser-induced breakdown spectroscopy or other optical measurement method will be used, or CARS, coherent anti-Stokes Raman scattering, can be used for measuring the temperature. But I would say the optical measurement method is typically less accurate compared to the sensor reading, because it is giving you the number indirectly. With most of the optical measurement methods, what you're actually measuring an indicator. For example, with the emission spectroscopy, maybe strength of emission lines or width of the emission lines can be measured, and that quantities can be correlated with the quantity you are interested in, like density or concentration. So your indicator is now correlated with the temperature or concentration, but the connection is quite weak. Okay? So there could be many different things involved with the physics, why this indicator is sensitive to the property you are interested in. So typically, the indicator would be the function of multiples of properties. Let's say you chose the emission line width as the gas density, okay? But the gas density, the line width will not be only the function of gas density. It will be also a function of temperature. It will be also a function of velocity, all other properties. But maybe the sensitivity of the line width would be high with, for the gas density. So in that case, you are choosing the line width as the gas density indicator. But still, this line width is also the function of other properties. So if other properties are changing, then definitely the line width will change as well. So the uncertainty is increasing. So that's why optical measurement is typically less accurate compared to the sensor measurement. So sensor measurement is also an indirect measurement, and we will talk about that later. But between the indicator of the sensor and the real property you want to measure, there is not very complicated correlations. So that is giving you typically more accurate measurements. So in other words, if you can measure something with a sensor, then use the sensor. Only when you cannot measure the property with the sensors, maybe the optical measurement would be the option, but accuracy would be worse. Right. So this is combustion heater. In the combustion heater, the temperature is typically 2000 or more than that, and the pressure can be still measured with a pressure sensor where the temperature is low enough. So your combustion gas will be produced, and maybe here some corners where the high temperature gas is flowing through, near the center region, then maybe the side order region, the temperature will be low. Okay? And the flow speed here should be very slow, maybe less than Mach 2 or Mach 1. So it is incompressible regime. So the pressure would be uniform everywhere. So you don't have to measure the pressure at the center where the temperature is so high. Okay? So that is your choice. But theoretically, you can make sure, maybe you can make sure that, but you assume that the pressure field is uniform. So you measure the pressure at a point where temperature is low enough so that your pressure sensor is not damaged. Okay? And you assume that that pressure is uniform everywhere. You can measure the pressure pretty accurately without an optical measurement method. Okay? And then maybe you are using the optical measurement for measuring a density at the location. Okay? Maybe at the center where temperature is high enough. Okay? Then you will have the density information and the pressure information, and then it will help you to extract temperature information. That's how most of laser diagnostics works. Laser diagnostics cannot give you the accurate information by itself in many cases. So you will have to combine the information from the sensors, and the sensor information is more accurate. So keep in mind that you are not purely or solely relying on optical diagnostics in many cases. I would say most cases. So sensor measurement is still very important. So you should learn about the sensors at first, and then on the worst cases, in the worst cases, you cannot measure the sensors. You will combine the measurement using optics or lasers. Okay? Right. So here's another typical hypersonic testing facility, which is called expansion tube. With the expansion tube, you don't have heaters. And the heating is now, in this case, done by the shock wave. So in the driver section here, you have a high pressure gas and you have a diaphragm. And for some reason, when the diaphragm is broken and the rupture of the using rapid pressure change. So driver section has high pressure and driven section has extremely low pressure. And due to the rapid pressure change, a shock wave will be produced. And the shock wave will produced at this location will propagate until the end of the driven section, and there is another thinner diaphragm. The diaphragm will be broken by the shock wave, and then shock wave will propagate through the expansion section. And this expansion section and the driven section will be filled with the test gas. The test gas will be heated up by the shock wave. As you know, shock wave is increasing the pressure and temperature simultaneously. So the test gas, which is stored in the driven section between the two diaphragms, will be heated up by the shock wave. And the shock wave is definitely moving at supersonic speeds. And although this is like tens of meters, it takes just only a milliseconds. Okay? So everything is happening within milliseconds. Okay, so this is another very typical uh, target unit optical measurement, because you should conduct the measurement within a millisecond. So everything should be done within a millisecond or even less than 100 microseconds. Okay? There are not many sensors that can give you the result within a millisecond. Okay? The fastest sensor will give you the result within like hundreds of microseconds. But with the optical measurement method, what you're doing is injecting photons and taking the photons that are coming out as a result of the photon-matter interaction. Okay, so traveling of the photons are quite fast, even compared to the shock wave. It's much faster. Okay? And the photon detector system has shorter response time. So that means even within 1 milliseconds, you can measurement like 1,000 times. Okay? So typically, the light propagates a meter within a nanosecond. In a nanosecond, within a nanosecond, you can make a measurement, for example, with the typical test section of 1 meter length. Okay? So tens of nanoseconds typically, or hundreds of nanoseconds, is sufficient for optical measurement. Okay? So far, any sensors cannot work at that short time period. Pressure sensor is working at 100 kilohertz. That is maybe the fastest sensor you can find. And 100 kilohertz corresponds to maybe tens of microseconds. But as I said, maybe 100 nanosecond is sufficient for a single optical measurement. Okay, so now you have seen two very typical situations where you have to use the optical diagnostics. First, high temperature and high pressure. And under these conditions, you don't have many options. You will have to maybe use the optical measurement. And maybe you will combine that with a sensor measurement result. And the sensor measurement is typically giving you a better result, you can say. And while in other cases, for example, like expansion tube facility, if you have to measure some property within a very short time period, then maybe the optical measurement method is the only option you can choose. Okay. All right. Here's another possible heaters you can use for generating high temperature and high pressure gas. That is arc plasmas. And arc plasmas can generate like temperature above like tens of thousand kelvins. So it is extremely high temperature. So most of the devices will melt down. Okay. So accommodating arc discharge or plasma discharge in a vessel is quite challenging. So the other option you can choose is generating the arc plasma for a very short time period. Or you can isolate that with a magnetic field. You can choose that, but it's not the main interest of this topic. Anyway, so this guy is increase the temperature maybe above 4,000 Kelvin. And you can mix the gas with a colder flow here to produce 4,000 Kelvin and 10 bar gas. And that's the system I have used when I was in the United States. So anyway, so let's say now you produced 4,000 Kelvin gas, but at 4,000 Kelvin, many of the molecular species should be dissociated, and some molecules will be internally excited. Okay? So this guy maybe will require some time for reaching an equilibrium state. Okay? And this 4,000 Kelvin temperature is not uniform, maybe. Okay? So some molecules should be excited. Some molecules should be dissociated to form different species. Okay. Then to produce this hypersonic flow, you will have to heat up the gas up to 4,000 Kelvin. And as you have seen here, the only option you can reach the 4,000 Kelvin is the use of plasma discharge. And in the plasma discharge, you will have large number of that are exciting the molecules. So the internal energy of the molecules or the dissociated radical concentration should be measured. They cannot be measured under this high temperature condition or highly energetic situations. There are not many ways of measuring those quantities that are required for this hypersonic testing. Okay. So in that case, you have to use an optical measurement method. Okay. So here is the extreme case: high speed, high pressure, high temperature condition with an arc heater. Okay. So that is the only way of testing the hypersonic vehicle. All right. So it is just like that. So let's say this system is typically not that big, but making a big wind tunnel takes always more money. So we made a small scale hypersonic vehicle, and we have an arc heater that is producing like 4,000 Kelvin high temperature gas, and it will be pressurized, and through the CD nozzle, it will be emitted, and the Mach number would be maybe 3 to 9, and the stagnation temperature could be up to 4,500 Kelvin. But the static temperature, as I have explained before, would be between 150 and up to 500 Kelvin. Okay? At high altitude, where this high-speed vehicle is flying, the typical temperature is between 200 and 300 Kelvin, so much actually lower than 300 Kelvin. It is quite cold condition, and the pressure is much lower. Like at 30 kilometers from the ground, the pressure in the atmosphere is only 1 to 2 kilopascal. You know, the one atmospheric pressure is like 100 kilopascal. It is less than 100. It's quite low pressure. And at low pressure, at low temperature, the gas is flowing at Mach 9. So that corresponds to the pressure of 10 bar and 4,000 Kelvin. So although the atmospheric condition at that high altitude is low temperature and low pressure, you should produce high temperature and high pressure gas here. And for measuring the quantity of this highly energetic gas in the upstream region, you will need an optical measurement method. And in the downstream region now, pressure and low temperature conditions, but still the gas is flowing at very high speed, like Mach 10 corresponds to the, maybe 3 kilometers per second. So for the 1 seconds, the gas will travel 3 kilometers. So that is quite fast flow. And under these high speed conditions, there are not many ways of measuring some properties of this gas. So optical measurement is the only option you can choose. Okay. So let's say your sensor is measuring some quantity for like 1 millisecond. 1 millisecond means your gas is only moved like 3 meters. So in this case, the flow speed is 3,000 meters per second at least. And for 1 second, for 1 second, 3,000 meters per second. For 1 millisecond, it is moving like 3 meters. So 3 meters. So your gas is moved like 3 meters. The length of this aircraft is just like 60 centimeters. So for 1 millisecond of the sensor measurement time duration, your measurement target has been already moved like much further downstream, away from this beacon, like 3 meters away. So it is not viable. Your sensor speed should be at least like megahertz. 1 megahertz corresponds to 1 microsecond. Okay, 1 microsecond. Even for the 1 microsecond, your gas is moving a significant distance. Okay, for optical measurement, as I said, you need only 100 nanoseconds. Then your gas will be almost stand still there, so you can conduct quantitative measurement, even with this high-speed flows using a laser diagnostics. That's why you need a laser diagnostics. Okay? Right. So the system configuration is not very important, but one very important thing here is that you should know about the control system of your target system. Okay? In this case, the control unit is placed here, and you should exactly know when the high-speed gas is produced and when the gas is flowing through the model vehicle. Okay? And that's why, because you should program the timing of the laser diagnostics. Okay? So let's say your laser firing time should be accurately programmed to measure the property at a proper time instance. Okay? So this system is working for about 1 second, and for 1 second is long enough, but If you want to operate it for a longer time, your arc should be extensively cooled because the temperature, typically local temperature, exceeded 10,000 Kelvin, and your system will start to melt down or evaporate. Okay? So, because over the short time period of the test, you should program the measurement execution time instance very carefully. So, to program the measurement properly, your measurement system should be directly connected with your control system. So, your control system should be connected with your optical measurement uh, devices. So that's why your control system, I mean, you should understand the control system at first to conduct the optical measurement uh, properly, okay? Because it is mostly used for short time period and fast experiments. Okay? As an example, so you have a model vehicle that looks like the window. So optical access window is required for your measurement. Okay. Then what kind of optical access window should be used for your measurement? That depends on your measurement technique. Okay. So in this case, we have used the fused silica, and fused silica is transparent for UV to visible range. So if your light source is in the UV to visible range, then you can use fused silica or quartz crystal windows. But if you want to execute laser absorption spectroscopy, like for CO2 or H2O, and some CO2 and H2O lines are near the IR region, so fused silica window should be fine. But if you're using the deep IR or mid IR range wavelengths with several micrometers of wavelengths, then fused silica or quartz window is not transparent to that wavelength. Okay, so you should use a sapphire glass. It's much expensive, much more expensive. But anyway, so depending on the light source or depending on the laser diagnostics you are going to use, your access window should be different. Let's say you are doing the experiment or measurement with only the visible light, then maybe plastic windows or typical glass windows can be used as well, because those are transparent in a broad area of visible range. So for visible range measurement, maybe you can use any transparent optical access window. And the other thing you have to think about is how wide the access window should be installed or designed. So in this case, you want to see the flow structure inside the whole vehicle, then you will need a large optical access window. But for example, if you need just zero-dimensional measurement, then maybe you will need a small hole with a transparent window. Okay? So that is sufficient maybe for a zero-dimensional measurement or one-dimensional measurement. But for two-dimensional or three-dimensional measurement, you will need a larger optical access window. Okay? So this optical access window is required for confined experiment. If you're doing a very basic fundamental experiment like atmospheric conditions with candles or small burners without confinement, then your optical measurement is becoming much simpler without optical access window. Once you have an optical access window that will reflect and refract the laser light or the light source, the photons will be scattered on the surfaces and your measurement will become much more complicated. But in most of practical optical measurement environment, there should be a pressure and temperature difference across the optical access window. For example, your laser systems or sensors should be placed outside of the harsh flow conditions. For example, like in engines, you want to measure something in the engine. So you should not put diode laser into the engine. It should be outside. And then your light source, like diode laser or pump laser, should be protected from the high temperature, high pressure, or high speed gases. Okay? So that's why you need an optical access window. The optical access window is protecting your optical systems at first. So to protect your optical systems and detectors maybe, you will need to use an optical access window. So learning about the property of the optical access window is becoming quite important when you're designing optical measurements. So that's what I want to say here. And here is some examples of the measurement, optical measurement. Okay, so this is the flow structure that has been measured with a planar laser Rayleigh scattering. So you are basically injecting a two-dimensional laser beam from the back to the upstream. So these are the flow structures inside this aircraft vehicle. So laser beam is from the back to the front. It is two-dimensional by a combination of lenses like cylindrical concave and spherical convex lens. You can make a thin laser beam out of a circular small laser beam. So circular small laser beam can be transformed using a combination of lenses to make a two-dimensional thin laser sheets. And the thin laser sheets that is transformed using a lenses, using a combination of lens, will be injected through this vehicle. Okay? And then that laser beam will cause scattering. So in this case, we have injected CO2 into the flow, and the CO2 will be clustered or condensed by the rapid temperature drop with the CD nozzle. In this case, it was Mach 4.5, and your temperature is dropped so fast. Although you have injected gases, CO2, into the upstream region, while the high pressure CO2 containing air is expanding through the CD nozzle, the temperature will drop so fast, and the flow will be accelerated. And we have seen that using a simple equation before. So temperature is decreasing and the kinetic energy is increasing because of the energy conservation, and the temperature dropped. So the CO2 is becoming a small fine particles, and that particle size is on the order of tens of nanometers. Tens of nanometer is smaller than the 1/15th of the wavelengths in this case. So that's why we call that in Rayleigh scattering regime. And we will learn about the Rayleigh scattering later. But anyway, Rayleigh scattering is an elastic scattering phenomena. So the photon energy will not be changed. If you're injecting 532 nanometer photons, and then the photon will collide with the small particles of tens of nanometers, and then it will be scattered, and the direction of the scattered, collided photon will be random. So that's why we call it scattering. Scattered photons will be collected at a direction, and if the scattering intensity is high, then that means the particle population at the location is high. Okay, if the CO2 particle population is high, then the location has higher gas density, because your CO2 initially injected in the gaseous phase will be uniformly distributed in the upstream region where the high pressure gas is stored, and then it will expand to be accelerated. Then it will be uniformly still distributed, but the particles will be uniformly distributed at first. But as it comes into the inlet of the vehicle, a shock wave will compress the air. So by the shock compression, high pressure region will appear. And this is color-coded image of the two-dimensional Rayleigh scattering. So you can clearly see the shock structures and the shock-induced boundary layer separation and laminar to turbulent boundary layer transition is clearly investigated with this two-dimensional Rayleigh scattering measurement method. So this is quite nice visualization technique to show you where a shock wave is placed and where the pressure is increased and where the turbulent boundary layers develops, etc., and where the shock wave interacts. Okay, and this flow is becoming turbulent, and flow speed is so high, and the Reynolds number is on the order of millions. So it is quite fast and three-dimensional flow. So we move the laser sheets from the center plane of this vehicle model, center plane, and then we move the plane toward the side wall. So you are seeing a different slice at 1 millimeter from the center plane, 2 millimeters, and up to 19 millimeters. and the half of the width is 20 millimeters. So from the center to the side wall, it is 20 millimeters. You can see near the side wall, the flow structure is quite different. Okay, so this is a kind of a way of three-dimensional measurement using a two-dimensional optical measurement method. So planar laser Rayleigh scattering method is a two-dimensional optical measurement method. But you can make multiple slices of that flow field using this one, and then you can reconstruct the three-dimensional flow field. And that's a typical trick we are going to use for many optical measurement methods. So you do the two-dimensional measurement and making multiple slices, and that is maybe used for reconstructing the three-dimensional structures. So if you see each slice, so at 1 millimeter away from the center, you see a clear structure of the sharp waves, and near the sideward structures, and you see just a turbulent and random flow structures, because your flow now from laminar to turbulent transition has been occurring at the location. Okay? So laminar to turbulent transition is happening at this location, as you can see from the side view, and now your laser beam is immersed in the turbulent boundary region. So that's why you're seeing just random complex turbulent flow structure inside. Okay. So this can be used for reconstructing three-dimensional flow structures. And now we have intentionally made a turbulent flow in the upstream region. So your flow structure in the free stream looks quite different. So even in the free stream region, you have highly turbulent flow. So there's no laminar boundary layer region here. So highly turbulent flow is coming into, so free stream look with the same flow conditions, like same Mach number, same pressure, and same temperature conditions, your flow structure could be quite different. Okay? So that is why we are using this optical measurement method. And the measurement time in this case is about 100 nanoseconds. So you are looking at a snapshot of the turbulent flow. And turbulent flow evolves and is changing its structure within a microsecond sometimes. That means the frequency of the evolution could be like megahertz or maybe kilohertz. Then you should take the image within like hundreds of microseconds. Although the frequency of evolution is like kilohertz, then 1 microsecond is the period. But to see a clear snapshot of the flow structures, you should maybe take the pictures within 100 of microseconds. Okay, so particularly in this case, the flow speed is Mach 4.5, and flow speed is so fast and it is highly turbulent, and the evolution of the flow structure is quite fast. So to take the snapshot of the flow structure, your measurement time or laser diagnostics time should be quite short. So the only option you can use is the optical measurement method in this case. Okay, here's another similar example, which is the use of planar laser induced fluorescence. Okay? Planar laser induced fluorescence. In this case, you're using inelastic collision. Okay? With the elastic collision, your photons that are injected into the region of interest will be simply scattered, and the energy will not be absorbed by the matter inside. But in this case, for example, in this case, you are injecting the laser beam at 283.4, maybe 284 nanometer wavelengths, and that photon energy will be easily absorbed by a very specific radical species, which is called OH, hydroxyl radical. And this OH radical is produced only in a very high temperature reaction regions of the combustion reactions. Okay, so this is a kind of marker of a high temperature region, or the marker of the combustion reactions. Okay? Look at here. So with the exactly same system, you are injecting a laser beam now, which has a wavelength of 283 nanometer, and that photon will be exceptionally well observed by the OH radicals. So most of the, uh, I mean, not most, the largest portion of the photons that are injected into in this case will be observed by the OH radicals. And then these OH radicals will be excited. And then this excited OH radical will try to go back to its original state to be equilibrated. And then photon will be produced. And that photon will have a wavelength longer than 283 nanometers. In this case, it's roughly 400 nanometers. So now wavelength of the photon is now increased. So that means some portion of the photon energy is now observed and dissipated by the molecules. Okay? As the wavelength decreases, the frequency of the electromagnetic wave will be increased. And the frequency is exactly proportional to the photon energy. So shorter wavelengths photon will have higher energy. So 283 nanometer photon will have higher energy. But some portion of this photon energy will be absorbed by the OH radical, and it will be dissipated later. And 400 nanometer photon will be produced by the excited OH radicals. And those 400 nanometer photons were collected and imaged to show you this PLIP image. PLIP is the planar laser induced fluorescence. So the laser, 283 photon containing lasers, will induce the fluorescence of OH radicals. The fluorescence is at 400 or 410 nanometers. That's longer wavelengths. So only 400 nanometer photons are collected using an optical filter, and that is giving you this image. So you are basically looking at the distribution of the OH radicals. So very bright region implies that your OH concentration is higher because more OH has absorbed your 283 nanometer photons and emitted 400 nanometer photons strongly at these locations. That means OH radical concentration is higher at this location, and then combustion reaction is maybe more active at this location, and the temperature is higher in this region. So your flame marker, that is OH distribution, is now imaged at different locations, different slices. In the near sideward regions, you see a diffuse high temperature region or reaction region. But near the center region, a shock wave that is produced by the jet injection. Oops, I didn't include that. But when you inject the jet that is producing a strong shock wave, and the shock wave will increase the temperature and pressure behind. So by the shock wave, a strong combustion reaction is occurring here. And in the downstream region, it will be well mixed with the incoming air and the fuel that are now circulating behind and mixed with the incoming air. And then combustion reaction is occurring in the downstream region. And by combining these different slices, you can get three-dimensional flame structure. So that is a way of three-dimensional measurement. So three-dimensional measurement will require the large amount of data bus. So the large amount of data should be collected, and those should be transferred for record. So in this case, data transferring or data bus is another critical issues that are limiting the three-dimensional measurement. So in other words, as you have seen here, three-dimensional measurement is quite difficult, challenging, and expensive. So only in the case really three-dimensional measurement is required, you are going to planning the three-dimensional measurement. And there are some other limitations of this kind of three-dimensional optical measurement method exist, and I will introduce that in the next class. All right, so today we have seen some examples of the optical measurement method, okay? Some reduced models and some practical reasons why optical measurement method has been used. Okay? So until the next class, please think about some specific cases the optical measurement method is required. So I mean, most expensive measurement method would be the three-dimensional optical measurement. If you have some interesting cases requiring three-dimensional optical measurement method, then maybe you can suggest, and maybe you can make a team to solve the problem. What would be the best way of the optical measurement? That is, I hope that that could be an initiation of your research project for this semester. Okay, so we have seen some high speed, high temperature, and high pressure measurement conditions, and we have seen some other examples of this measurement in two-dimensional and three-dimensional optical measurement. It looks like these, and three-dimensional information can be provided with this expensive measurement. Okay, all right. We will talk about other optical measurement methods a little bit more, and then we will get into the real topics we're going to study this semester. Okay. Any questions? You can type in questions also, and you can maybe ask questions in Korean. 질문 있으면 해주세요. 채팅창으로 치셔도 되고요. 네. 아무튼 시간이 됐으니까 수업은 여기서 마치는 걸로 하고요. 제가 잠깐 더 기다리고 있을 테니까 질문이 있으면 뭐 타이프를 쳐줘도 좋고 아니면 음성으로 얘기를 해줘도 좋습니다. 그리고 팀 짜는 거에 대해서는 조금 더 생각을 한번 해보세요. 한 5명 정도, 뭐 5명 넘어도 됩니다. 뭐 10명까지는 괜찮아요. 너무 많으면 같이 일을 하기가 힘드니까 뭐 5명에서 6명 정도면 제일 좋을 것 같고요. 그렇게 팀을 꾸려서 지금 오늘 보여준 이런 좀 상당히 챌린징한 경우긴 하지만 어떤 케이스를 정해서 그 케이스에서 여러분들이 무엇인가를 제외한다면 그걸 왜 제외하는지에 대해서 한번 초기에 생각을 해보면 좋을 것 같아요. 타겟 시스템을 정하고 팀을 짠 다음에 무엇을 왜 이렇게 비싼 메저먼트 테크닉으로 제외하는지를 한번 생각해 본 다음에 그걸 정리해서 저랑 첫 미팅을 할 때 소개를 해주면 될 것 같습니다. 네, 그럼 오늘 수업은 여기서 마칠게요. 수고했습니다. 오늘 수업이나 지난번 수업 소리가 잘 들리셨나요? 제가 다음 수업부터는 한번 녹화를 한번 해볼게요. 제가 좀 말이 빠르다는 사람도 있더라고요. 네, 알겠습니다. 네, 고맙습니다. 그러면 다음 주 화요일 날 다시 만나는 걸로 하고요. 보강 수업에 대해서 그때 한번 다시 얘기를 해보도록 합시다. 네, 고맙습니다.